So now I'm going to talk about the problem I want to solve. The problem is this is made out of ductile iron and it's very heavy, and every pound I can take out of it is a cost savings to me. So I want to minimize certain dimensions as much as possible and still have it work in its stressed state. And so I know that this wall thickness right here, that's something that I can make thinner and save some weight. And this flange thickness is something I can make thinner and save some weight. And this wall thickness here is something I can make thinner and save some weight. The question is, how do I do that? How do I do that? And I do that using something called finite element analysis. And so I'm going to show that to you just to see how it works. And that's going to be our next step. And our final step will be to use the parameters, right? This class is all about parameters. To use those parameters to handle all of these conditions effectively and efficiently. Okay, so here we go. I'm going to do a finite element analysis. I do that from my modeling screen, modeling tab, and there it is way over there, stress analysis. And we can work on all sorts of parameters. We can work on the von Mises stress or the deflection or this or that or the other thing. I just want to have a safety factor. And I want the safety factor to be above 2. Okay? And I also know that this product is meant to carry 150 psi, and the standard test for this is twice load. So I'm going to have to load this with twice 150 psi, 300 psi, pushing on the inside surface of water, and I want to make sure it's strong enough. It's got a safety factor above 2. So I go to my stress analysis to do that. Stress analysis. So I'm going to create a study, and I'm on 2 screens, so it always puts it on the wrong screen. And I'm going to do what's called a static analysis. In other words, it's going to keep stressing itself until it can't stretch anymore. And that's going to tell it what to do. So it's a static analysis. Nothing is dynamic or moving. Static analysis, so I'm going to click OK. It's right down at the bottom. Right down there. Static analysis, and then down to the bottom, OK. And it started a study for me. And I can give it a name and all that other kind of stuff. Now I want to always check my material to see if I've got it right. That's something else I can change if I want. It's taking it as ductile iron. It could be that if things are wrong and don't work, I can change the material. But right now, I'm just going to leave it alone because it looks right. Iron. Ductile iron. Then I always have to hold this in place somehow. And the way this is held in place is this flange is bolted to another flange. And I could be more careful about that, but I'm just going to fix this. That essentially can't move. That surface is bolted tight to another surface. So I'm going to fix that surface right there. Left click. And then it's always telling me, is that what you want? Okay, okay. And I can add more, but that's okay. So I'm going to say that's okay. And it puts a little, let me zoom in on this, puts a funny little sign there. That says it's fixed right there. Fixed constraint. And it matches the one up there, fixed constraint. Then I have to apply my pressure. Now pressure loads against the side evenly in all directions. That's what a pressure does. So it's going to be 300 psi, and it's going to be on the top and on this chamfer and on the cone and on that, and it's even going to be on this surface right here, and I just know that because I'm the designer for this. Okay, so that's where the water can go to put pressure against this, and so we're going to put those pressure items there. Okay, so I've got a material, I've got a pressure, and I've got a fixed location. So now it's time to simulate. Simulate. Says ready to run. Yes, let's try it. Run. And it did not give me an error, and it came up with this cool picture where most things are blue, and this is von Mises stress. So, you know, in KSI, thousands of pounds per square inch. So where it's blue, it's 0.03 thousand. So it's like not much at all. Where it's green, it's like maybe 2,000 pounds per square inch. Now those numbers don't mean much to us because we're not material science people. We don't know what the limit is for this. So we're just going to go right to safety factor. There's the safety factor right there. And oh my gosh, it's all blue. It doesn't even give me a minimum. It's all so high. This is supremely strong. Supremely strong. I don't see any red anywhere. I don't even see any green anywhere. And it'll usually give me a minimum number. So this thing is hecka strong. So that's good. And I can write a report on that. It comes up down here, and I can write that report. I'm not going to right now, but I can write a report. So I go, okay, I can reduce weight. I can do that. And I'd like to just see if I can get rid of like 20 or 30% of the weight. So that means I have to know how heavy this is. File, properties, physical. And I'll just, doesn't say I need to update it, so here it is. So it's 6.86 pounds. Mass, 6.86 pounds. 6.86. So I'm going to write that down somewhere because I'll need to figure out what that is. As a matter of fact, I'll do it right here. What's my target? My target is 6.86 times 20% reduction would be 0.8 left. If I can get to 5.5 pounds, I'll be good. 5.5 pounds. So let's go to our parameters and see what happens if we cut this wall thickness down. The wall thickness was cone wall thickness, there it is, 0.25, and it was pretty hefty. Let's go 0.18. Let's just change it to 0.18 and rerun that stress analysis. Stress analysis, everything's still right. So let's simulate. Run. And come back to safety factor. Oh, now there are some that stresses again. Safety factor. There we go. It's still all blue. Oh my gosh. That is incredible. So I can go down to a 0.18 without a problem. That's cool. And I can keep guessing and guessing and guessing till I get to the minimum number that I think I can use. Okay, and that's called the guess and by golly method. And then I can also take this thickness and start working some material out of that thickness. And I can take this wall thickness and work some out of that. Okay, and you can go through those and do those by hand and see what you come up with. Just reducing the parameter, reducing the parameter, reducing the parameter until we get to the point where we've got it good. But let's see what we saved. How much did we save there? File, iProperties, physical. Now I have to update it because I made a change. 6.16. So I got a ways there. I made a good start. I'm trying to get to 5.5. Okay. That is how you use parameters and stress analysis to determine the most effective size. It's called size optimization. Size optimization. Okay? And I'll come back and give you another video on how to make this a little bit more automatic and a little bit more systematic.